네.
Nice to meet you all. I am Jung Gyoo-yeol. So the thing that I'm going to cover today is marine biorefinery. Biorefinery is just like oil refinery. So the term is from the oil refinery, but it is just the contrary. So it is using the biomass in order to extract some useful material. So oil contribute to greenhouse gas emission. And that comes from coal, gas, and oil. And gas and coal are used to generate power, and oil is used for transportation and petrochemical material production. In order to reduce the GHG, we need to see petrochemical industry. 80% of oil is used for fuel, and 20% is used for naphtha to make plastic products and other petrochemical products. To reduce the use of this petrochemical fuels, then we will have to replace the oil. If you see the chemical formula of the oil, it is composed of hydrocarbon, so the element is C and H. If you see biomass, plant-based biomass, they also include CHO. So if we properly convert the carbon, hydrogen, and oxygen and can replace the oil, then we will be able to use biomass instead of oil and sustain the petrochemical industry. So that's the goal that we have. So if you look at the bio industry currently, the most used feedstock is corn. So around 1.2 billion tons is produced as for corn, and that's used for food or biofuel feedstock. As you can see on the right side, many industry verticals use corn and make various products out of corn. And a part of that is used for fuel. So as mentioned, 1.2 billion of corn is used across the world, and a part of that is used for fuel, which is around 100 million ton. And 100 million ton out of 4.5 billion tons of oil takes a small amount. So this means that the corn is not enough to replace the oil. So the alternative is non-edible biomass, for example, sugarcane and cornstarch. If we can use sugarcane and cornstarch, then we can replace the oil. So that's why we have done a lot of research on this, but the process was quite complex, so it was difficult to attain economic feasibility. To solve that issue, one idea we came up is turning the eye to the ocean. And highest productivity in the ocean is by brown macroalgae. In order to nurture or cultivate biomacroalgae, we don't need any land, new land or fresh water. So there's no need for additional water supply. And in the aquaculture industry, we don't need any fertilizer because we can use oceanic nutrients as a fertilizer. So there is less negative impact on the environment, yet bigger economic impact. So this is the macroalgae production across the world. China, Korea, Indonesia, Philippines, many Asian countries are cultivating brown macroalgae. And then the total production across the world based on wet weight is 30 million tons. So the amount is quite small. The reason behind this is because the algae is only used for food. So that's why the production volume is not enough. if we are to extract the petrochemical feedstock from the algae, then we will have to increase the production volume. So let's check whether that is possible. This is the kelp map, global kelp map. So this means that there is enough habitat of kelp that we can use. So it is highly promising. So if the kelp seabed is used to cultivate or do aquaculture, then we can produce the kelp to replace the oil. And as you know, we have 100 years of aquaculture history. So water depth of 200 meter or less, then we can use it as an aquaculture form of kelp. Then if we can convert that area to do aquaculture of kelp, then we can use approximately 220,000 square kilometer. Then that will be around 6% of the maximum global demand of oil. Likewise, the brown algae productivity per unit area is quite high, and they can effectively nurtured. So in terms of feedstock volume, it will be okay. The next question is why we cannot use brown algae as industry feedstock. It is because in order to use it for industry, there should be starch or starch-like element. But in case of brown algae, there is not enough starch or carbohydrate. Instead, the alginate, which are not metabolized, are contained in brown algae. So the usability was the problem of using brown algae as feedstock. So we have the synthetic biology toolkit and technology. So we studied the microbe and raised the microbe. We can metabolize the alginate within the brown algae. So as mentioned previously that brown algae was not used because the alginate was not metabolized. If we can edit this function of brown alginate, then we will be able to use it in the industry, and that is called synthetic biology. So synthetic biology means that we can engineer the biosources or bioresources just like we engineer machines. And that depends on how we engineer the gene or genetic data. As mentioned, we need to design the genetic data and edit those genetic data. And genetic data here means the protein, the performance of the protein. And the process is quite complex, but we need to have that forecast on the functionality of the protein. And there are around thousands of processes that is entailed to the gene expression to make protein, so it is very difficult to forecast. So what we did was to study the biology and forecast the amount and the quality of the yeast. And if we can do so, we could edit the genetic data. And by doing so, we could re-edit the genetic data of brown algae so that it can metabolize the alginate. As Korea raised a lot of brown macroalgae, the government decided to do a research on this. In 2002, we won a research project to study brown macroalgae to transform it into useful feedstock. So likewise, we took the first step in order to utilize the synthetic biology to develop alternative feedstock. But in order to replace the current petrochemical or oil industry, then the ample amount should be supplied in order to replace it. And then we will have to have a mass amount of aquaculture farm for feedstock. So for vast aquaculture production, then we will have to study the agriculture methods. In the U.S., the DOE, Department of Energy, started Mariner program in 2016 in order to develop an automated aquaculture production of brown algae. So this year, KIMST and U.S. ARPA-E, which is under the Department of Energy, signed a memorandum of understanding to apply the automated aquaculture technology to the coastal area of Korea. And the goal of this collaboration between DOE and MOF is to apply the aquacultured brown macroalgae to be applied in various industry verticals. So the goal of our research is to reduce the price of brown macroalgae to be down to $80 per ton. If you think about the oil price, which ranges between 50 to 100% dollars, then I think the price parity will be reached. See, to do the mass scale aquaculture, then first we will have to select the right seed or breed and then have the automated production capability as well as supply chain and other production of biochemicals which can attract many value-added chemical production. I think this is the future of marine biology. In case of Korea, for a long time, we have accumulated know-how and knowledge on aquaculture, and that's why DOE selected Korea to collaborate. And we have high technology prowess or status of biology. For example, CJ and GS Caltex, they use biomass to produce plastic products, and they're ready to hit the market by mass production using this technology. So as such, we have the supply chain and are ready to generate or make new industry based on this new technology. So ultimately, if we succeed in developing this automated aquaculture technology, then the next step is this. We look forward to establishing or making a new marine biochemical complex, just like an industrial complex. Then first is to have that technology and build an industrial complex and then have a consolidated bioprocessing. Then that will guarantee sustainability of the bio industry based on green technology. In result, the GHG emission coming from petrochemical will be able to be reduced using such technology. So fishing village in Korea is, the living condition of there is not good because they only produce the food sources. But if the fishing villages can contribute to producing more added value petrochemicals or biochemicals, then the rural area development and economic development of those regions will be reached. So this is the end for my presentation. And the people you see on the screen are the researchers who are tirelessly working on this project. We are working on a small budget and tight schedule. We are making a lot of efforts to meet that. Thank you for listening.